Okay, so welcome back. More factorizations. So the next speaker is Joel Lewis from George Washington University, and he will tell us about reflection factorizations of single cycles in linear and unitary groups.
Thanks to the organizers for having me. It's been really nice to be here and meet some people whose names I know through papers, but who I've never met before. So this title of this workshop, I use the words combinatorial, enumerative, and algebraic a lot to describe my own work, but never in this order. In particular, I really think of myself as a combinatorialist. And so I want to tell you 4 stories that are all related to each other and build on each other. And because I think of myself as a combinatorialist, I really want to start off with the symmetric group because it's the best. So here's a simple combinatorial question. Take an n cycle in the symmetric group, so I'll call it a long cycle if it's an n cycle in Sn, and write it as a product of transpositions, right? And okay, so first question is like, how many do you need? And it's pretty easy to see that you need n minus 1 of them because at the identity you have n 1 cycles, and then every time you multiply by a transposition, you either merge 2 cycles or split one. So to get down to a single cycle, you need to merge at least n minus 1 times. But then, because we've got the word enumerative, you should ask how many different ways can you actually do that? And I don't believe in suspense, so here's the answer. So there are n to the n minus 2 ways to do this. And this is a wonderful combinatorial number. It counts lots of things, but in particular, maybe the first interesting thing that anybody ever knew it counted was trees on n labeled vertices. Let me prove this theorem for you using Dinesh's proof. Dinesh has nothing to do with Denef from Friday, but so here's the proof. All right, so I'm going to count trees. But rather than counting trees on labeled vertices, I'm going to count labeled trees. So trees on n labeled vertices where in addition, I put a linear order on the edges. And so there are n to the n minus 2 of the tree vertex labeled trees, and then each of them has n minus 1 edges, which you can order in any way that you want. So the number of these labeled trees is n to the n minus 2 times n minus 1 factorial. And now let me turn each of these trees into a transposition factorization. And the way I'm going to do that is I'm just going to take for each edge, if the edge connects vertices A and B in the tree, I'm going to convert it into the transposition that interchanges A and B, and then I'll multiply them in the order that the linear order of the edges. So like here's my tree. So it has 5 edges. And I've ordered them, so the first one connects vertices 4 and 6, so I turn that into the transposition 4, 6. And the second one connects 4 and 5, so I turn that into the transposition 4, 5. And then I multiply them in the order of the linear order. You can convince yourself that when you do this, you always get an n cycle, because it's a tree. And in fact, every transposition, so you don't get your n cycle. Right? We started off with a particular n cycle, and you get some n cycle. But in fact, you get every possible factorization into n minus 1 transpositions of every n cycle this way. And all of the n cycles are all conjugates, so they have the same number of factorizations, and there are n minus 1 factorial of them. So you get n minus 1 factorial times the number of your factorizations, and then the n minus 1 factorials cancel. All right, so this is Dinesh's proof of this wonderful factorization result. And this result is the first result in a really rich story in the symmetric group. If you sort of generalize this by sticking with permutations, but now say replacing the long cycle with other permutations, you get the Hurwitz numbers, which have a whole bunch of different interpretations in enumerative geometry, like counting maps on surfaces. And Hurwitz was originally interested in this enumerative problem of counting Riemann surfaces with poles of prescribed monodromies and things. And you can generalize it in other ways. You could consider factorizations of longer length, or you could do other other factors other than transpositions, and you get this really rich story in like the Gould and Jackson school and connections with symmetric function theory and all sorts of good things. Yes. Yeah, I'm sorry. So that the factors act transitively on the numbers 1 to n. It's like connected. Like the point is, if you have a permutation with distinct cycles, you want the factorizations not just to factor each cycle separately, but so that the factors act transitively on the set 1 to n. That's right. That's right. Yeah. The graph of the factors should be connected.
If you remove that, does it become harder?
If you remove transitive, it becomes easier. Yeah, because then you can just like factor each cycle independently, and you just get separate independent copies of the previous problem. Yeah. So the interesting thing is to keep that transitivity, which for the n cycle is automatic because the n cycle is itself acting transitively. Yeah. Oh yeah. This bullet point is like one that I stuck in there because people I talk to use this word. It's for people's names. The ELSB formula. It's an integral formula for counting moduli spaces of curves, but that is actually the extent of my ability to say something intelligent about that bullet point. Yeah. Yeah. Sorry. Okay. So this is one really rich, deep story about the symmetric group, but I don't want to go into more detail on that. I want to tell you a different story next, which is to replace the symmetric group with a larger family of groups and take this question and carry it to a more general context. And so there's a really natural way to do this, which is that the symmetric group, if you take any field, then take f to the n, and Sn acts on that vector space by permuting coordinates. And that's a linear action. And when you think about that as a linear action of the group, and you ask, okay, but who are the transpositions? They are exactly the reflections in that linear action. And for me, today, reflection is just going to mean an element that fixes a hyperplane pointwise. You could add extra conditions on there, but it's not gonna matter. So in particular, the transposition that transposes the ith and jth coordinates, it fixes the plane with equation xi equals xj. And so anytime you're thinking about the symmetric group generated by transpositions, you can generalize that to just thinking about a reflection group. So this is any finite group of linear transformations that is generated by its own subset of reflections. And so if you make this generalization, then our original question, which is asking how to count an n cycle in Sn as a product of the minimum number of transpositions and how many ways can you do that, becomes a new question where you're asking how to factorize some element in a reflection group as the product of the minimum number of reflections. And to get an analogous or generalizing question, you need to ask who's the n cycle, right? That's really the only extra piece of information I need to tell you to generalize this question. If you're working over the real or the complex numbers, there's a totally standard answer to this question, which is that the n cycles in Sn are exactly what are called the Coxeter elements. And I don't want to tell you what a Coxeter element is in general for a real or complex reflection group, but I just want you to know that in Sn, they are the n cycles. And so that's the thing that you should put in the blank there. And ask how many ways are there to factor a Coxeter element in a real or complex reflection group. And I still don't believe in suspense. So here's the answer to this question. So I think this was first solved in the real case in this like letter from Deline to Luenga. So it's like not a publication. And then in the complex case by Bassis much more recently. And so here we're factoring a Coxeter element as a product of n reflections, which is the minimum number, and you get this nice answer, which has this wonderful product structure similar to the n to the n minus 2 structure. You've got the size of the group down here, n factorial h to the n. Okay, and when you want to check that this gives you back the Hurwitz-Danish result, you have to know that the rank of the symmetric group is n minus 1, and then you just plug these things in, and you get back exactly the previous results. This is just a straight up generalization. And this result is also the jumping off point for a very, very rich theory of the Coxeter-Catalan combinatorics. This counts maximal chains in the lattice of W non-crossing partitions, whatever that is. So there's a wonderful, rich story here going back 30 years or more, which is also not the story I want to tell you. So this is story number 2. So the story I want to tell you next is the same thing, but now I want to do a different field. All right, so because that's real and complex, but what if you want to work over some other field? And so here's my definition of reflection group again. And so this is a theorem. It's a little embarrassing to call this a theorem. This is a thing that I teach my linear algebra 1 students every year, right? Which is that every invertible matrix is a product of elementary matrices, and elementary matrices all look like this. And you know, if you compute the fixed space of each of these things, it's n minus 1 dimensional. And so that means that if you take the general linear group over a finite field, and by n invertible matrices, that's a reflection group, because here are some reflections and they generate it. So you can ask this same question that we had before. So these are the first two stories, and then you can try to transpose this question into the general linear group. And so okay, so your group is general linear group. Reflection is going to keep meaning reflection, and then the question is, who is the element? Who in the general linear group should you be factoring that's analogous to the n cycle? And so now I really mean analogous. In the real or complex case, that was a generalization. Here I'm not really generalizing. I'm taking a Q analog in some sense. And there's a good answer to this question. So and they're called Singer cycles. And so, all right, what is a Singer cycle? Well, first, GLN contains irreducible elements. So elements that don't stabilize any proper non-trivial subspace of the vector space. And a Singer cycle is just of those irreducible elements. The Singer cycles are the ones of maximum multiplicative order. And there are lots of equivalent characterizations of these elements. It's a really nice family of elements. So they all have order q to the n minus 1. And in fact, they're the only elements in GLNFQ that have order q to the n minus 1. They act transitively on the non-zero vectors in the vector space fq to the n. They're also the elements that have one of their eigenvalues as a cyclic generator for the multiplicative subgroup of fq to the n. And okay, so those are all characterizations, and they're also all sort of reasonably clear analogies to the way an n cycle behaves in Sn, right? So the n cycle doesn't stabilize any proper non-trivial subset of the numbers 1 to n, and that characterizes n cycles. In the symmetric group, this order, like if you take the symmetric group, like if you think about the size of the symmetric group, it's built up as this product, and the sort of factor that you are multiplying by each time is the order of an n cycle. And the same thing is basically true in GLN, that the size of GLN is just the size of the smaller GL times this order of the Singer cycle. Okay, I'm fudging a little bit on the powers of Q, but when you do Q analogs, you get used to just sort of putting powers of Q in gray and hoping no one notices. You know, the long cycle acts transitively on the points 1 to n, and they have eigenvalues that are cyclic generators for the nth roots of unity and in the complex number. So I want to say like you should believe that if you're going to take a question about the symmetric group and try to translate it to a question about GLNFQ, that if your question about the symmetric group involves n cycles, then your question about GLNFQ should involve Singer cycles. Now, if you actually wanted, I don't know, I like doing computations with things, and these characterizations don't really tell you how to write down a Singer cycle, but if you want to like go to Sage and like actually count something involving an actual Singer cycle, here's how you should write it down. You know, FQ to the n as a vector space over FQ is FQ to the n after you choose a basis, and the multiplication by a fixed element in FQ to the n is FQ linear. So you get an embedding of the multiplicative subgroup of FQ to the n into the general linear group GLNFQ by choosing a basis, and the Singer cycles are exactly the images of the multiplicative generators under all possible choices of bases. Okay, I said concrete, that's not super concrete, but like to make that like really concrete, choose your cyclic generator, write down its minimal polynomial over FQ, and then write down the companion matrix of that polynomial, and that's like a particular nice choice of basis that lets you write these things down, and then you can do whatever computations you want. So these are, you can get your hands on these things pretty easily. Okay, so Singer cycles. So our original question was counting factorizations of an n cycle in Sn as a product of transpositions. Then we did Coxeter elements in real or complex reflection groups as a product of reflections. Now, the Q version, Sn becomes GLNFQ, transpositions become reflections, long cycles become Singer cycles, and question number 3, story number 3. So this is a question that when I was a postdoc in Minnesota more than 10 years ago, that's horrifying. Vic Reiner asked me this question: how many ways can you do this? How many ways can you factor a Singer cycle in GLN as a product of the minimum number of reflections? And together with Dennis Stanton, we solved it, and here's the answer. And you know, the thing that I would like to observe is, again, looks really nice. It looks really nice. It's just a power of the order of the Singer cycle, q to the n minus 1 to the n minus 1. Okay, so that was 10 years ago. Yes. Yeah. Okay. So as I will say later, I don't understand why these answers are all nice, right? I mean, I understand why the symmetric group answer is nice. I don't understand why this is a nice number, but I do pretend to understand why. I mean, here this is basically n, right? Why is this n minus 1 instead of n minus 2? It's because the rank goes up. Because GLNFQ is rank n, whereas the symmetric group is rank n minus 1. So this is like the rank minus 1. So that's why the exponent is 1 larger. I mean, that's why like my proof is not gonna explain that, but that I will at some point say something about some of the proofs of some of these results. Yeah. Sorry? Yeah, so a reflection for me is just a linear transformation that fixes a hyperplane pointwise. No, yeah, that's right. So, right, which is why I didn't put for the symmetric group that it was orthogonal, because I don't want to impose anything for GLNFQ. Yeah, so this includes the transvections. It includes things with all sorts of different eigenvalues. Yeah. Sorry? Yeah, so for complex reflections, so for a finite real or complex case, like you can do this averaging thing. So if you don't impose orthogonality in the real case, or if you don't impose whatever the adjectival form of unitary is in the complex case, you can like put it in there by doing an averaging thing. So like you don't need to add it as a condition because you can get it after the fact. Not true over a finite field because you can't divide to do the averaging. But yeah. Okay. All right. So these are the 3 stories I've told so far. And now for sort of the last many years, it's been rolling around in my head this question, which is, that was one particular reflection group over a finite field. But there are lots of reflection groups over a finite field, right? I mean, I didn't just do a single complex reflection group. We did all of them. So for the last 9 or 10 years, I've been wondering, like, what about other reflection groups over finite fields? Can you do the same thing? And so again, the first question is, okay, but who are you factoring? And I think this is probably the right answer, which is you should just take a Singer cycle. Okay, so what's a Singer cycle? It's an irreducible element of maximum order in the group. Now, not every irreducible reflection group over a finite field contains irreducible elements, but fine. So we'll only ask about the ones that do contain irreducible elements. That's okay. So take a reflection group over a finite field, and that contains a Singer cycle. And here's a question: how many ways can you factor it as a product of reflections? And I cannot answer this question in full generality, but I can answer it in a lot more generality than I could 10 years ago. So I want to present to you the answer for groups in what I am going to call the linear and unitary families. And let me tell you who the unitary groups are, and then I'll tell you what I mean by the linear and unitary families. Okay, so unitary group. So on one hand, if you have a vector space over FQ squared, those can have Hermitian forms on them. So this is like it's not bilinear, it's linear in the first coordinate and like conjugate linear in the second coordinate, where conjugate for FQ squared means raising to the qth power. So you can take the group of invertible linear transformations that preserve this thing, and that's the unitary group on V. And as a matrix group, by an appropriate choice of coordinates, that's exactly the set of n by n matrices whose, I've said over the algebraic closure of FQ, but really all the entries end up in FQ squared, such that the inverse is the transpose, and then you take the coordinate-wise conjugate. So this is just like the complex unitary matrices, except conjugate means qth power, entry-wise qth power. So this is the general unitary group. These things are almost all reflection groups. For whatever reason, when q equals 2 and n equals 3, it's not, but all the rest of them they contain reflections, and they're generated by their reflections. They contain irreducible elements when n is odd. So when n is even, something funny happens with FQ squared having you can always find sort of bad subspaces or good subspaces, depending on your point of view, that are stabilized because of the field thing, because of evenness. But when n is odd, these contain Singer cycles, again, except for the weird one. So okay, so this is another reflection group over FQ, and then the special unitary group was the determinant one elements in there, and that is also a reflection group over, sorry, I'm saying over FQ, which is a lie. I guess it's over FQ squared, but over a finite field. That's also a reflection group. And okay, so this is our questions again, same questions as before. And so the reflection groups for which I can answer this question are what I'm calling okay, so the linear family are sort of all of the groups that lie between the special linear and general linear group, or the unitary family, all the groups that lie between the special unitary and general unitary group. All right? And so for all of those groups, if you take the ones that contain a Singer cycle, so that means in the unitary case that n has to be odd and also not the case n equals 3, q equals 2, the number of factorizations of the element as a product of reflections is exactly the same wonderful answer. Okay, so this is story 4. Let me tell you about the proof. This is how the proof should go. All right. So I should now define for you a Q analog of trees, which for some reason should be counted by a nice formula. And then I should give you a nice map surjective map from factorizations to trees with a predictable overcounting. And then we should be able to divide. And at q equals 1, this should degenerate into the symmetric group case, and you should be able to see, and there should be an extra factor of n somewhere because there is. So that's how this proof is supposed to go. All right, if you can figure out how to do any part of this, please let me know. I've tried a lot, all right? I can't do any of these things. So what can I do instead? Well, what I can do instead is I can finally use the word algebra, right? Which is that all questions of this form, all questions of the form that I've discussed so far, there's just a machine that answers them. And the way the machine works is if you know enough character theory, if you know enough character values of your group, then here's the answer. Right? It's a sum over the irreducible representations. You need to know the dimensions. You need to know the character values on the element you're factoring. You need to know the character values on the allowable factors. Here this is like, I'm factoring an element as a product where, the first factor comes from the first set and the second factor comes from the second set and so on, and the last factor comes from the last set, under the condition that the sets of allowable factors are conjugacy closed, which transpositions and reflections are always unions of conjugacy classes in these groups. So it's like just a matter of understanding the character table. Okay. Now, I mean, of course, like understanding character tables, even of the symmetric group, like depending what you want to know, that can be quite hard. So let me if you wanted to reprove Dinesh's result not nicely, but using this idea, in the symmetric group, you would need a list of irreducible representations. You would need their degrees. You need to know the character values on the long cycles for this term, and then you would need to know the character values on the transpositions for these other terms. And you can do this because the irreducible representations of Sn are indexed by partitions. Their degrees are given by the hook length formula. Character values are given by the Murnaghan-Nakayama rule, which is a little hard to work with, but for long cycles in particular, it's very nice because it tells you that the character values are 0 except for a hook-shaped partition, so where there's like one long part and then a bunch of ones. Those are the only time the character values on a long cycle are non-zero, and so that kills off most of the terms in this sum. Right? You have a sum over all partitions, but unless it's a hook shape, you have this factor of 0, and so it just goes away. And then you need character values on transpositions, and you can work it out, right? Okay, so if we want to do this over a linear or unitary group over FQ, I need the same 4 pieces of information. I need the irreducible representations, I need their degrees, I need the character values on Singer cycles, and I need the character values on reflections. So let me tell you about that. So the first thing is I do not need to understand the representation theory of all of these groups, because all of these groups are contained in either the general linear or general unitary group, and the reflections in each of these groups are a union of conjugacy classes in the bigger group. So I can just do the representation theory in the bigger group. So I actually only need to understand the representation theory of GLN and GUN, which is really handy. All right. Okay, so this is what I said before in SN, indexed by partitions. I don't need to know every row of the character table because lots and lots of characters just aren't going to contribute. In GLNFQ, okay, instead of being indexed by partitions, the irreducible characters are indexed by multi-partitions. So this is an assignment to every irreducible polynomial over the relevant field of a partition subject to this weight condition that the degree of the polynomial times the size of the partition added up should be n. This is a much, much larger and more horrible family of things. Still, I mean, you can write it down, but worse, much worse. When you want to compute these characters, in GLNFQ, you've got Harsh-Chandra induction sitting around, which I understand more or less how it behaves. And for the unitary group, you have the analogous thing is Deligne-Lustig induction, which I'll say slightly more about on the next slide, but fundamentally I don't understand it. But luckily, I mean, the very first thing we do is that luckily this thing, the version of Murnaghan-Nakayama, is still there for you. All right, so in particular, even though you have this much larger family of characters, most of the time for an irreducible element, the character value is 0. And the only exceptions are when the multi-partition is primary, so it's got a single polynomial that contributes, and moreover, the partition associated to that is a hook. So that's our sort of first, like, just technical result that says, okay, you could do it this way because you don't really need to know the whole character table. You just need to know this relatively tame family of character values. All right, the degrees are already known. They look like the hook length formula, but you put some Q's in. The rest of the character values, okay, so for GLN, these can be computed using, all right, this work of Green and Harsh-Chandra induction, and like things appear that are called the Green polynomials that are like, you can get your hands on all of this stuff. Like the Green polynomials, they're in chapter 4 of McDonald. They appear also as change of basis formula between Hall-Littlewood polynomials and some other symmetric function. You know, they're things you can get your hands on fundamentally. Deligne-Lustig induction, you get similar formulas, and they involve these things called green functions. And the definition of a green function is a trace of a certain action on the L-adic cohomology of some variety. And this is why this took me 10 years, because I don't understand that, right? I mean, I just don't like know what any of those words mean. And like computing these things is really hard. Computing these things in general is really hard. And then there's this miracle. And it's called Enola duality. And the miracle is that if you want to know something about the general unitary group, what you should do is forget about the general unitary group, go ask your question about the general linear group, and then at the end put in minus Q instead of Q, and that's the answer that you're looking for. All right? So this is like a meta theorem. And like the precise statement of this theorem in our context is that these green functions that I don't understand, the ones that we need are all evaluations of appropriate green polynomials, which I do understand when you plug in minus q. And so you just never have to know what L-adic cohomology is, which is great. And so then you can get the remaining character values this way. And so that's it. Then you have all these ingredients, and you go back to this formula, and you plug in, and this is what comes out. And you do several pages of not insightful computations, and at no point in the intermediate stages does the answer look nice, and then miraculously something nice comes out. I should also say that if you just look at GLN and GUN, the answer for GLN is this number, q to the n minus 1 to the n minus 1 that we had before. The answer for GUN is q to the n plus 1 to the n minus 1 when n is odd. And this is itself an instance of Enola duality. So I could have just cheated and said, oh, but just put in minus q, and that would have worked too. So this is our theorem. One thing I want to observe about doing it this way is that it doesn't really matter how many factors you add here. If you add more reflections, you don't need to know more representation theory. The same character values, you can make the factorization longer. So for essentially the same amount of effort, you can answer the question not just for the minimum number of reflections, but for any number of reflections, you can get the answer right away. And so this is the answer. So for any of these groups, this is the number of factorizations of a Singer cycle as a product of L reflections. Is this sort of wonderful sum? I mean, okay, it's an alternating sum. You've got some normal binomial coefficients. You've got some q binomial coefficients. You've got your n to the L minus 1 out front. This epsilon, this is doing the Enola thing for you. In the linear group, it's 1. In the unitary group, it's minus 1. And then this is taking care of which group are you in, is you need to know how many conjugacy classes of reflections there are in your group, which is basically how many different determinants there are in your group. So that has to appear somewhere. And so that's where it appears. And so this is just for free. You just get this along the way as an intermediate step towards getting that c to the n minus order of c to the n minus 1. So I don't know. I don't understand this formula at all. I mean, it's beautiful. I'm very happy with it, but don't ask me to tell you what it means. All right. So I want to end with one open question, which is, that's not a complete list of all reflection groups over finite fields. I mean, I don't think anyone knows a complete list of all reflection groups over finite fields. People do know the list of irreducible ones. People do know even the list of irreducible ones that contain a Singer cycle. So there is some list of groups for which you could ask this question. But the obvious next thing to ask about are the orthogonal and symplectic groups. So there are a bunch of different families of orthogonal groups over finite fields. Only one of those families contains irreducible elements. It's the minus type. There's no standard notations for these things, but this is one of the notations. So the minus type of even rank, and then there are the symplectic groups also contain them. And I've done some computations, and I think this is the answer. The representation theory of these groups is way harder. There's the step 1 is I said, okay, these things are indexed by multi-partitions, but there's no version of that step 1 for these groups. Nobody has a good indexing of the irreducible characters for orthogonal and symplectic groups. So if you want to solve this problem, I don't think, well, if you're a lot better at representation theory than I am, maybe you could do it this way. But my understanding, I mean, Ryan is a lot better at representation theory than I am, and he was the one who was like, no, this is hopeless. So on the other hand, if you can prove this conjecture by, say, combinatorics or something, that would actually tell you things about character sums in the orthogonal and symplectic groups, which would be interesting things about those character sums. So So I think this is true. Why? I mean, that's really, you know, I mean, this is the open problem, but like the real open problem is like, why are these things nice? Is a real mystery. It keeps happening. I don't fundamentally understand it, but I think it's really neat. Thanks so much for listening.
Thank you very much for the wonderful talk. So we have lots of time for questions. So, yes, Amrit.
So how important is it that you look at the single cycle here? Because for SN you had a formula for transitive.
Yeah, no, that's a really great question. So, I mean, okay, so I told you the indexing of the characters somewhere, yeah. So of course that's also the indexing of the conjugacy classes. So there are like a lot of conjugacy classes in GLNFQ. Yeah, I've played around with this a little bit and like made some guesses about what are some other elements that might be nice, and what should the definition of transitive factorization be for GLNFQ? Like, do you really want it to be that it acts transitively on the non-zero vectors, or maybe you just want it that the factors actually generate the whole group? I've tried a few different things and have not so far succeeded in finding another question that has nice answers as far as I can tell. But I think it's a really natural question, and I feel like blundering around just sort of blindly trying things hasn't worked for me. So a person would need a good idea about how to go find it, and my things I thought were good ideas about how to go find a version of that haven't worked out. So I do feel like there should be a thing, but I don't really know what the thing is that I'm looking for.
Yes, please.
You showed us a number of results for subgroups of groups of the form GLN, FQ, GU, and FQ. So these finite fields arise as residue fields of compact discrete valuation rings, and these rings have many more finite quotients. So I wondered if there's any indication of a theory like yours producing similarly nice formula I talked with you before, groups such as GLN or GUN over Artinian rings of length 2 or 3 or arbitrary L.
Yeah, that's a wonderful question. I have no idea. I mean, I haven't ever looked, but I don't have a piece of paper. So can you repeat that question to me later when I have a piece of paper so I can write it down and do so? Yeah, yeah. No, that's a great question. I have no idea. As far as I know, no one's ever looked.
All right. Yes, please.
Yeah, okay, so the going way back, where is it? Yeah, okay, so I didn't talk about the proof of this result, but the proof of this result is sort of inductive. Like you take your group, you look inside an appropriate parabolic subgroup, and you can induct in some way by finding Coxeter elements inside the smaller group somehow. And so a natural idea is to try to do that for the general linear group or general unitary. I've tried that a little bit, and I've had a grad student try it a little bit, unsuccessfully. One thing that is going on in this story is that there's this, okay, so if you ask like, who are the elements that appear as intermediate steps in this factorization? You know, so like you take a factorization, take a partial product of it. Who are those elements? And they have a nice characterization in the real and complex case, the parabolic Coxeter elements. And you can characterize them, and that lets you do this inductive thing. And if you ask me like, who are the elements that appear on the way to a Singer cycle? they don't seem nicely, like all sorts of stuff. All sorts of stuff appears. I don't have good control over it. In particular, things appear that don't behave at all like Singer cycles. So there doesn't seem to be that good inductive structure. I wonder about like the orthogonal or symplectic group. Like there it's a little more rigid, and like maybe there could be something like that. But if there is such a structure in GL that would allow you to like build on, okay, like smaller Singer cycles or something Singer like, I haven't seen it. It doesn't look like it to me, which is part of the reason it feels like I'm forced to do this thing. But that would be really nice. I mean, that might be a good way to give a proof that was more illuminating about why the answer is nice. But I haven't been able to do it.
Right. Any others? Yes.
In the so I am, all right, very much not an expert. My understanding from, right, sorry, going all the way to the end. Okay, so my understanding of the representation theory is like I have learned from my collaborator, and what my impression is that like you just don't have as nice, like the irreducibles just aren't labeled in an equally nice way in those groups. You can look at the, I mean, I've done like small amounts of computation, and my memory from these small amounts of computation is like that it's not, at least for the, the small sizes that you can do on Sage or GAP or whatever, that you don't have the same really massive amount of sparsification happening in those groups as you do in the unitary and general linear case. But if you have reasons to believe otherwise, I would be interested in hearing about them and talking about them. This is a part in which I am definitely not expert at all.
Okay, yes, please.
Like parking sequences, like there's such thing here, kind of enumeration of parking sequences.
Yeah. I mean, right. There's this wonderful. I mean, yeah. The story of n to the n-2, and even in the real and complex cases, you have this non-crossing partitions and parking functions, and like you have lots of nice combinatorial things sitting around. I would love such a thing. I would love such a tool to attach that would give you something to explain these numbers. Yeah, we don't have any such objects.
Right. So unless there's more pressing questions, I think let's thank the speaker again.
Thanks.